Now that you have seen what a logistic equation is and how to solve a differential logistic equation and the different forms of a logistic differential equation and equations, we are going to look at real life situations. At the end of this lesson, you'll be able to write a logistic equation to model a situation. Wait, we're going to jump right into our example. A conservation department releases 1,200 brook trout into a lake. It is estimated that the carrying capacity of the lake for the species is 20,400. After the first year, there are 2,000 brook trout in the lake. Question A says write a logistic equation that models the number of brook trout in the lake. So if it's asking for a logistic equation, not a differential equation, we know that we're going to use the formula y equals L over CE to the negative KT plus 1. All right, so what we are going to do on this one is let's plug in our L, and I think that's all we're going to have. Our carrying capacity is 20,400, so we're going to have y equals 20,400 over CE to the negative KT plus 1. All right, now very similar to when we solve exponential growth problems, first of all, we need to find our C, and then we need to find our K, and then when we're done, we actually get to solve the problem once we found our missing variables. All right, or actually they're constants. What we are going to do here is use the information given. First of all, it says they released 1,200 brook trout, which means there were 1,200 at time equals 0. So I'm going to have 1,200 equals 20,400 over CE to the negative K times 0 plus 1. That will give me 1,200 equals 20,400 over, this would end up being e to the 0, which is 1. So on the bottom, I'll end up getting c plus 1. From here, I'm going to cross multiply to solve for c, so I'm going to get 1,200 times the quantity c plus 1 is equal to 20,400. I will next divide both sides by 1,200 instead of distributing. And when I do that, I'm going to get c plus 1 is equal to 17. And then subtracting 1, I'll get c is equal to 16. All right, so far now I have y equals 20,400 over 16 e to the negative kt plus 1. All right, now I'm next going to use, after the first year, there are 2,000 brook trout in the lake, so now I will have 2,000 equals 20,400 over 16 e to the negative k, because t is 1, plus 1. Again, I'm going to cross multiply just like I did in the previous finding c. We'll get 20,000 or 2,000 times the quantity 16e to the negative k plus 1, and that will equal 20,400. I will divide both sides by 2,000, and when I do that, I'm going to get 16e to the negative k plus 1 will equal 10.2, and then from here we'll divide both sides. Well, actually we're going to subtract 1 first. How about? We'll get 16e to the negative k is equal to 9.2. And then we will divide both sides by 16. So I'll get e to the negative k is equal to 9. Oh, actually, if you divide that, that does work out to a stopping decimal, terminating decimal. We'll get 0.575. And so I will take the natural log of both sides, and we get to bump the negative k out front. So I'll get negative k is equal to the natural log of 0.575. which means k is going to equal negative natural log of 0.575. So now I just need to rewrite my formula, which I will think I will do up here. I've got y equals 20,400 over 16e to the, and notice that this says negative k, so since k is already negative, this will actually be a positive ln 0.575 t plus 1. So that is my logistic equation. Part B, find the number of brook trout in the lake after 8 years. All right, we already know the formula is y equals 20,400 over 16e to the ln 0.575. T this time we get to let be 8, and that will be plus 1. So when I plug in 8, I'm going to get 17,118 trout. And this time I did decide not to round to 3 places because you can't have a part of a trout. Okay, part C, when will the number of brook trout reach 10,000? So this time I would like to know, what would my t value be when my y value is 10,000? So 10,000 equals 20,400 over 16e to the ln 0.575 t plus 1. Okay, and just like we did in all the other examples, we'll multiply by 10,000, we'll cross multiply. We'll get 10,000 times the quantity 16e to the ln 0.575 t plus 1 equals 20,400. I will divide both sides by 10,000. And when I do that, I'll get 16e to the ln 0.575t plus 1 is equal to 2.04. If you do divide that, I do believe that's what you'll get. And then we'll subtract 1 from both sides. So now I'll get 16e to the natural log of 0.575t is equal to 1.04. And then from here, we'll divide both sides by 16. So we'll get e to the natural log 0.575t, which is equal to 1.04 over 16. I'm not going to write this as a decimal because it doesn't turn out nicely, and we don't want to have rounding errors when we're done, so leave it exact. And then from here, we'll take the natural log of both sides. And so when I do that, we'll have, we'll bump that out to the front. So I'm going to have the natural log of 0.575t is equal to the natural log of 1.04 over 16. And then to solve for t, we'll just divide both sides by the natural log of 0.575. And when we do that, we should get t is equal to 4.939 years. All right, part D says to write a logistic differential equation this time that models the growth rate of the trout population. All right, the general form of a logistic differential equation is dy dt equals ky times 1 minus y over the carrying capacity, which is L. Right, so we're going to plug in what we do know from this equation. We know dy dt is equal to, we found that k was equal to the negative natural log of 0.575. We'll keep our y as y, and then we'll have 1 minus y over the carrying capacity was 20,400. So that would be my differential equation that models the situation. And there we go.